In this example, we're going to do hypothesis testing, the p-value approach for a one population mean when the population standard deviation is known. So in this example, we have test the claim that the average body temperature of healthy adults is 98.6 degrees Fahrenheit and a 0.62 degrees standard deviation. A sample of 106 people found their average body temperature to be 97.2 degrees Fahrenheit. We're going to use a 0.01 level of significance, and we're going to use the p-value approach to hypothesis testing. So I have a template set up for us for the 6-step approach to hypothesis testing, p-value approach. And what we're going to do is always in that first step, identify the given values in symbolic form. So we're going to read the question and look at the numbers. We say that the claim is that the mean is 98.6. So that's all healthy human adults. Mu is equal to 98.6 degrees Fahrenheit. And then it says we have a population standard deviation is given to us. We label that as sigma is 0.62 degrees Fahrenheit. And we have a sample size of 106, so n is 106. And of those 106 people, it was known that their body temperature, so the sample mean, was 97.2 degrees. And we're going to use a level of significance of 0.01. So in step number 2 of the p-value approach to hypothesis testing, we're going to identify that claim, write the null and alternative hypothesis, and we're going to remember that the null hypothesis must always contain equality. So the claim was given to us in this first statement was that the average body temperature of all healthy human adults means equals 98.6 degrees. Now that does contain equality, so since it does contain equality, it's going to go in the null hypothesis. We're just going to restate the claim there. The claim has to go either in the null or alternative depending on if there's equality. And since our claim had equality, we're going to put it there. The opposite of equals is not equals, 98.6. So the opposite symbols of each other from the null and alternative hypothesis. Now we're going to calculate the test statistics. Since we have a claim about the mean when sigma is known, we're going to be using z is equal to x bar minus mu, sigma over the square root of n in the denominator. So we're just going to fill all that given information that we found in step number 1. We found that the mean was 97.2. The mean of the population is 98.6. We're going to subtract that out, and then we're going to divide that number by 0.62 over the square root of n, which was 106. So doing that calculation out, we get negative 23.25 as our test statistic, rounding off 2 decimal places because it's z-score. And it's okay to get a negative. It just means that we're on the left side of 0. And then in step number 4, we have to determine if it's a 1 or a 2-tailed test. And by the alternative hypothesis, if we have a non-equal sign, that's 2-sided. So I would shade in the 2 sides, the left side and the right side. So the right tail and as well as the left tail. So it's going to be a 2-sided test. Now it says use the test statistic. What we got is negative 23.25. That's going to be our z test statistic. That is on the left side of 0, left side of center, so we're going to plug that in. Now what we're going to do is we want to find the p-value. Now the p-value is going to be the sum of these shaded regions. The p-value is always the shaded region that we shaded there. So we're going to go to our z table that we have. And remember, the first column, first row is our z-score. And inside the body of the table is the probability of being in that shaded region. So we got a test statistic of negative 23.25. So we're on the left side, and symmetry was the right. So I can look up the positive values and then use symmetry to tell me the left side. So if I looked up 23.25, the positive version, I'd get over here. And then by symmetry, I can say it's the same thing on the left side. So I'm going to look up negative 23.25, but you'll see our table doesn't go any higher than 3.50 and higher. And you'll notice all these values are 0.0001. So since our value of 23.25, or by symmetry on the lower side, negative 23.25, is on the left side, we're definitely in that 0.0001 area. So the area in the right side would be 0.0001, and by symmetry, the area in the right side would be the same as 0.001. So the sum of those two areas that we shaded there is 0.0001 plus 0.0001 or 0.0002. That is our p-value. So it's the probability of being in that shaded region. Now, since we have our p-value, we're going to determine that critical value and rejection rate is determined by alpha. And it says if our p-value is less than or equal to alpha, then we're going to reject HO. And if our p-value is greater than alpha, then we're going to fail to reject HO. So we have to see how our p-value, that 0.0002, is related to alpha. Alpha was 0.01 in our question at the top there. So we want to see which one is bigger, which one is smaller, and clearly the p-value is smaller than alpha. So 0.0002 is less than 0.01. So it says if that's the case, if our p-value is less than alpha, we're going to reject HO. And then in our final concluding statement, we've already decided that we're going to reject. It's kind of like a fill in the blank statement here. Then this is the harder piece where we have to decide is there or is there not sufficient evidence. Now we said we're going to reject HO in step number 5. So it's like I'm rejecting my claim that's there. So we say there is not sufficient evidence. And then we're going to fill in that level of significance. Alpha is 0.01 to suggest that, and then we're going to restate the claim exactly the way it was worded at the top, that the average body temperature of healthy adults is 98.6 degrees Fahrenheit. And that is a hypothesis testing p-value approach for one population mean when sigma is known.